So in our wave on a string lab, we saw that the geometry of the string, which on a guitar is held fixed at the bridge and at the fret, determines what waves are possible. Any wave that's got no motion in those two places is okay. These large standing waves only exist for certain frequencies because you need to be sending them in at the exact right frequency that when they reflect off the boundaries, they overlap themselves and build up. You need to have that kind of constructive interference. So we've gone through the patterns of that. Essentially, the lowest frequency wave that fits in, the one bump wave, the fundamental. On a guitar string, multiples of that are all allowed too. In a real guitar string, if you pluck it, it's going to play all those notes at once. And that's why there's that nice rich sound. So when you pluck a guitar string, it plays all the allowed frequencies, or a lot of them. And if you played any of those frequencies, you would notice the guitar strings start to vibrate. That's how a sitar works. It has some strings that you don't pluck. They vibrate in response to the ones you do pluck. So this isn't just true for guitar strings. Any device that works by striking, plucking, or blowing on it, and a noise comes out of it, basically has the same thing. There's some sort of natural frequency, there's some wave that develops in the unique geometry, and what waves can go are limited by what the geometry is. So one of the most famous examples of this are these devices, which are called tuning forks. When you ding an object, you send that wave out. And if there's another object that has the same natural frequency, it will start vibrating. So if I grab the one I hit to stop it, you're still hearing the note because that one's playing. So what's going on here? I'm hitting this one. It's vibrating at its own natural frequency, which is 256 hertz. That wave is going out and making the other one vibrate because it had the same natural frequency. So this is how you can actually break a wine glass with sound. If you find out an object's natural frequency, you can play that note really loud, and that should break it.
So what we're going to try to figure out now is why different instruments play different notes. We're going to look at stringed instruments like guitars or pianos. We're going to look at organ pipes that are open on one end or open on both ends. And we're going to qualitatively look at things like tuning forks and xylophones and recorders. At the end of the day, what happens is we have to look at the geometry of the thing that's resonating and where it requires nodes to be. So let's take a look at these different instruments.
So I've taken two of the tuning forks, a small one and a large one, and I'm going to let you hear the notes they play. The larger one, if I give it a whack, plays that note. And the smaller one, that note. So the smaller one is higher pitched. They have numbers stamped on them. The larger one is 293.67 hertz. And we saw that was a low note. And the higher note was 493.88 hertz.
The geometry of tuning forks is complicated, but generally the larger they are, the lower the note, the smaller they are, the higher the note. You can also change the thickness of them. This geometry is really nice because it only allows typically one frequency, or barely one frequency, when you strike them, so they're really good for tuning a single note. Most of the resonators we'll look at in this class vibrate at a number of different frequencies all at once, specifically guitar strings and organ pipes. We'll take a look at them in just a bit and we'll figure out why they allow more than one frequency. Before we do that though, I want to take a look at one other instrument, a xylophone.
In the case of a xylophone, we just have different size blocks of metal that each have their own natural frequency.
With a piano, there's at least 3 ways to change the natural frequency of the strings. The first is we change the diameter, so you can see that as I move to higher notes, the diameter of the string gets less. You can change the tension, so we could tighten or loosen them with these pegs here. And you can change the length. This is hard to see just from looking at the top of it, but you can see it a little bit. And down below there's quite a difference. The lower notes are typically a lot longer than the higher notes, if you think of the shape of a grand piano. So playing a piano essentially is having the hammers hit different strings, almost like you pluck different guitar strings. In trying to figure out why any resonator plays a certain frequency note, it helps to re-examine the wave equation. So velocity equals wavelength, that's what this Greek letter lambda is for, times frequency. Meters per second equals meters times 1/second. So the thing that is set by the geometry of a resonator is its wavelength. If you think about a piano string that we just looked at, it's held at both ends. And that tells us that whatever's going on with the particular wave, it's got to have a node at both ends because it can't be moving there. This picture should show us what one wavelength looks like. It's two antinodes and 3 nodes. Think of this as like a sine wave where each part is buzzing back and forth. So we're going to first look at the geometry that's allowed for strings and what frequency strings can play. And then we're going to look at it for open and closed organ pipes. Notice that things like tension and thickness are not part of this equation. They affect velocity. The wavelength is the thing that can't change for any resonator because of its geometry. But by adding tension or by changing the thickness, that's going to change the speed of the wave, and therefore it'll affect the frequency, the notes that we hear. So here's a guitar string or a piano string, and as you can see, the only geometry requirement is that you have a node at both ends, because that's where the string is held. So a variety of waves can fit on there, and when you play either instrument, you get a variety of waves. That's why the tone sounds rich. The fundamental frequency, the lowest one that will fit, if you think of a full wavelength as being like a sine wave, which each is bulging back and forth, this would correspond to half a wave. So basically from here to here. So half a wave is the longest wavelength that will fit on a string. Then to find the frequency of that, you solve for wavelength and plug into the wave equation. And then you find what's called the first harmonic or fundamental frequency. But other waves called the overtones, or the second harmonic, third harmonic, fourth harmonic, also fit on here because, again, all you need is a node at both ends. And so if you go through the math, and you should do this independently, you can see that 2 times the fundamental should be allowed, 3 times the fundamental should be allowed, 4 times the fundamental should be allowed. Let's look at some other instruments that aren't strings and have different geometry requirements, not necessarily nodes at both ends. In the case of a woodwind, we change the length of a pipe, and that allows air to resonate in different size cavities, giving different notes. There's as much art and engineering in building instruments as there is science, and the techniques for making instruments that sound beautiful have been developed over many years with lots of smart people trying to figure out how to make instruments sound the best. Even this Dollar Tree plastic recorder is beyond what we're going to be able to study for wind instruments in this class. We're going to focus on 2 very specific types of wind instruments, namely organ pipes, whose frequencies they can play change depending on the length. And we're going to look at ones that are open at both ends and closed at one end. We'll start with ones that are closed at one end. So here's an extremely elegant organ pipe that I got out of the vending machine. But this shows us the geometry for an organ pipe that's closed at one end and open at the other. This made a note by me blowing over the lip of the bottle. So there's movement there. So that means there must be an antinote at one end. There's no movement here on the surface of the Pepsi, So that must be a node. So if you think about what waves are allowed to fit in there, 1/4 wavelength, the yellow one, so like this much of a wave is cool. Half a wavelength is not allowed because half a wavelength would have a node at both ends. So we don't expect the frequency corresponding to that for this bottle to resonate at that. But 3/4 allowed, that's this brown wave. So that would get you like up to here. A full wavelength, 4/4 is not allowed. But then another quarter wavelength on top of this would be cool. So there's less frequencies allowed for an organ pipe that's closed at one end. So only a quarter wavelength, 3/4 of a wavelength, 5/4 of a wavelength, only these odd multiples of a quarter wavelength work when you need to have a node at one end and an antinode at the other. So plugging those into the wave equation, you're left with only the odd multiples of the fundamental, the lowest natural frequency, end up playing for this type of pipe. In the case of an organ pipe that's open at both ends, you actually have to have an antinode at both ends because air will be moving in both places. So you actually have half a wavelength fitting in the pipe when you're using the longest possible wave. It's just a strange half wavelength. It's like the middle 2/4. But if you go through and check all the waves that could fit in there, you could have a half wavelength, you could have a full wavelength, you could have 3/2 of a wavelength. So at the end of the day, when you plug into the wave equation, you get back to what you have for wave on a string. You could have your lowest frequency, and everything else that's allowed is going to be a multiple of it. So here's, I think, the most important things to remember about the last few minutes of this video, which I know got technical. For both a pipe open at both ends and a wave on a string, you get the lowest frequency, which we call the fundamental, and you get every multiple of it as being allowed. For a pipe that's closed at one end, you only get the odd multiples. And to figure that out, draw a picture. A string has to have a node at both ends, an open pipe has to have an antinode at both ends, a closed pipe has one of each.